output. All right. There. Oh no. Oh, there we go. All right. All right. All y'all have these two things. This is the stuff for tests. I brought those notes to myself. Test. And then we'll get to this one. I guess I can go ahead and pass.
Tables that we'll get to shortly. We're going to play a sort of bingo, sort of, today.
And starting in with a little bit of a review. This is the last day we're talking about Part 4. The exam does cover all of Part 4, so we're wrapping things up.
That's on the 7th, right?
Mm-hmm. In lab next week. Is that the 7th? No, it's not the 7th. It's the 9th. Oh, let's go for green today. So in this, looking at how to deal with deflections, how to deal with beam stresses, going to kind of recap the overall problem-solving process. How do you approach these? And what is the first step, always, forever, and ever, always, ever? Free body diagram. You cannot run, you cannot hide, you cannot get away from statics. So step 1 is always a free body diagram. It's very similar. It's very similar, and we'll get to it kind of shortly. You can hand them up here. Find external reactions so you know all external forces. If you don't know the reactions, you don't know the whole picture of what's going on, and you're never going to get to the right answers. So what's the next step in trying to figure out what's going on with this structure? I got the external reactions.
What kind of structure is it?
Sorry, a beam in some sort of bending load. Beam in bending load. Next thing we're going to go for is a shear moment diagram. What's going on with the internal reactions? So internal reactions, and the typical way we do that is shear moment diagrams. That gives us the internal shear resultant and the internal bending moment as a function of x, so we can see where our worst case scenarios are. So get max or min of V or M. We see the failure point in X along the beam. All right. Then I guess there's a couple of different ways that you could go, but we now know where is our worst case scenario in X. We need a few other things, or the next thing we can look at is calculating stress. What kind of stresses result if we put a beam in bending loading? You get shear. How do I figure out the shear? That's torsion. That's the one. That's the one. Why isn't V over A the right answer? Why isn't V over A the right answer? Because that's a shear stress. That is a way to calculate shear stress. What does that give you? It gives you an average value. It gives you an average value. This lets you figure out the shear stress at some particular point in the cross-section. And why isn't TC over J the right answer, Brogdon? I don't know.
It's not forced.
TC over J. That's a twisting load, and we're talking about bending load. So that's right if you've got a drive shaft, but it's not right if we've got bending loading. All right, so we can do VQ over IT. The other kind of stress we can get is normal stress, and that one, Mr. Taylor, is which one? That's the one. Okay, you can get a minus my over I. So what's the missing piece of our puzzle? We have to get the cross-section moment of inertia before we can really go any further. Where do we get that? Depends. You might have one of those beam tables that says, okay, here is this I-beam, and it'll give you a little drawing that here's my I-beam, and this is one axis, and this is the other axis. Make sure that you pick out the I sub whatever, because this may be labeled X or Y, or it might be labeled Y and Z. Whichever way, make sure you pull the right one for the way that the beam is used in your loading scenario. So I sub whichever one is appropriate. So you get your moment of inertia. What if I just give you the dimensions? And it's some weird non-symmetric thing. That's for a single rectangle is your BH cubed over 12. You may have to use parallel axis theorem to figure it out. Maybe from a table, maybe it's given, maybe parallel axis theorem. Parallel axis theorem is for non-symmetric cross-section, and the details of it is you find the y-bar and you sum up the pieces, and it's the distance from the centroid and all of that, and it's on your little sheet and it's in your homework. So what's important if I'm saying where's my worst case, what if I have one of these non-symmetric cross-sections? You need to remember that you may need to check plus M, minus M, plus Y, and minus Y. If you have a non-symmetric cross-section, you need to check both your positive and negative bending moment and the top and the bottom of the beam, because it may not be gut intuition where the biggest stress is. So then what about this guy? What is this Q thing? It's your area moment. How do I figure it out?
It would be the area of the piece that you say is going to move, or the distance from its centroid to the centroid of action.
So it's as if you hold one piece stationary and move one piece. That A prime is the mobile area. And right, it's the Y bar from the component, or composite neutral axis to the centroid of the part that is the A prime. And what about this? Is that going to be this guy or this guy? It's this guy. It's the thickness of the actual material that would shear. All right, so that gets us through. Stop with the VPN. That gets us through finding out the shear stress. We may have, or the stresses. We may have shear stress. We may have normal stress. What about now if we want to know the deflection? How do we deal with that?
So, beam deflection. It will never be wrong to write the moment equation with the secret decoder ring of discontinuity terms integrate twice, get your constants of integration, and this works because the bending moment is equal to the bending stiffness times the second derivative of deflection. That's the fact that lets us do this. The other thing that you need to remember is what are the different boundary conditions. They give you part of the answer, depending on if you've got a cantilever or a simply supported case. There are geometric truths that give you some math. What are the geometric truths about a cantilever? It cannot move at the left end. It cannot move up and down at the left end. What else can it not do at the left end? It cannot rotate. It cannot rotate at the left end. What does cannot rotate mean? That's a slope. Some places you're going to see that as a V prime. You may also see it as a theta. It's an angle of rotation. So if you look at your new bingo card, you'll see that the slopes are noted as thetas. Okay, and we'll get to this a little more in a second, but it's a more complicated version of the thing you've already seen. The first column is the slopes, the second column is the deflections, and this third column is the elastic curve. What is that? We'll get to that shortly because we're not done with boundary conditions. I'm getting a little distracted. So we know that the deflection is 0 and the slope is 0 if we have a cantilever. What do we know about this? And I meant to actually draw this as the left end, sorry. We know that it can't move at the left end and it can't move at the other support. And what does this tell us? This tells us that both C1 and C2 are equal to 0. Generally, always true is that C1 is the slope at x equals 0 times the bending stiffness. That is always true. And C2 is always going to be the displacement at x equals 0 times the bending stiffness. So if your support is at the left end, C2 is always going to be 0. Now on the three dudes standing on a bridge problem that you may or may not have looked at yet because it's on an upcoming homework, the support is not at the end, so T2 is not at 0, but I will tell you that it's not going to be on the exam like that because that's just too much math. So C1 is the slope times EI, C2 is the displacement times EI,
And that is in the case of the beam, the supported beam, or the cantilever?
which this,
Those comments, yeah.
those are always true, no matter what.
Okay.
It's just that you know that the slope at x equals 0 for a cantilever is 0, which means C1 is 0. So these two statements are true no matter what the beam is. Whether you've got overhanging or supports at 0, it doesn't matter. Those things are always true. These things are true for those particular cases. All right. So we now need to segue into these tabulated deflections. So that's sort of the summary of the problem-solving process. When you have a beam in bending loading, what all can you get? You get shear stress, you get normal stress, and you can get the deflection. Once you get this deflection equation, which is a function of x, a function along the beam, equals stuff, how do you find out what the deflection is at any given location? You just substitute in your desired x. If you want the deflection at the free end and it's 8 feet long, you substitute in v equals, actually you would substitute v of 96 because it's typically going to be written in terms of inches, not feet. So, tabulated deflections. These are sort of shortcuts. And I want to say one thing about sign convention. We have said that x goes along the beam this way and y goes up. Okay, so we've had x and plus y. So for us, if you are standing on a 2x4 that's over a creek, what's your deflection? Your deflection, your v, is negative if downward. Okay, that's the sign convention we've used all along. Different people who tabulate these things can use a different convention. And one important one that you might run across in your engineering world is the FE manual. It's a very common reference tool. And instead of defining deflection to go along with the plus y, they define on the FE manual a quantity delta, which is a deflection, but they define it defined plus as downward. That's an important note that typically if you see a deflection that's a lowercase v, that's going to go along with the convention that we've used. And I'm just giving you a little warning sign that if you see deflection tabulated as a delta, typically that's going to be positive downward. And the reason they've done that is, I think, more of a civil engineering thing, that typically because gravity works downward, you usually are going to have deflections that are down. So instead of carrying around the negative sign, they just said, okay, let's just talk about it in terms of a positive number. So, but just to be aware of that sometimes you'll see things in terms of a delta instead of a lowercase v. All right, now getting on to tabulated deflections. So there's a lot of these common cases that the load is distributed across the whole thing, or the load is in the middle, or the load is at the end. And for these, instead of every time having to start from scratch and write the moment equation and do some integrals and people have tabulated and just jumped to the answer. So we've got a simple version here that will be the one that you're provided on the test, and we have a slightly more complicated version with a few more cases here on the bingo card. And what does it tell you? It tells you the maximum deflection is the second column, and essentially if you're dealing in the realm with small deflections,
It's just linear superposition. You can say I got one of those and I got one of those, and I'm going to add them up and I'm going to get the answer. And these are exact if your cases match perfectly to this. So this scenario that's here on this page that I think might be 58 in your book, it's a beam, it's a uniform load of 100 pounds per foot, and we've got a single 2,000 pound load in the middle. It is this standard W8 by 31. This 31, incidentally, means that that's its linear weight. And so we're going to add that to the distributed load. We know that the moment of inertia is the one that's about x, so that's 110. Another side note, this quantity S is another shortcut that they put in these beam tables that is the moment of inertia divided by this distance, which is c in the moment equation. So you can just pull this S out and do the moment divided by S, or you can just forget I ever said that, just remember MC over I, and you'll always be good. But this is a shortcut that they've already divided this beam by half its height. So looking at what this problem does, the 131 is because it's a 100-pound distributed load and the linear weight of the beam. And we can just break this into one of these and one of these. So you look on your handy-dandy bingo card and you find the appropriate cases that look just like what you've got. So for the distributed load, which equation do we need? We do not have a bingo. Okay, what's 10 giving you? 10 is giving you a slope. And 29, what kind of connection is 29? It's cantilever. So we actually need, which one? 11. So we need one of this, which is minus 5 WL to the 4th over 384 times the bending stiffness. We also will need
2.
Bingo. Yeah. We also need one of these, which is a minus PL over 48 EI, and I forgot the cubed. And from there, it's just a plug and chug. So what is W? W is 131. What is the length? 24 feet times 12. So we end up, where's my cheat sheet over here?
You don't need to convert.
You need to convert your W as well. So W is 131 pounds per foot, which is 10.917 pounds per inch. The length is 24 feet, otherwise known as 288 inches. Bending stiffness is 29 million psi times 110 inches to the 4th, which is 3.19 E9 pound inch squared. And then we plug it all in and we say V, and I'm going to call that DL from the distributed load, ends up being 0.3066 inches downward.
So that VI, that was like a special one. So
It's just that product, the modulus times the moment of inertia, is a thing that we refer to as bending stiffness.
is that tabulated in the island thing? Or is it not?
No, because it's this. E is tabulated for the material,
An I is tabulated for the cross section, so they don't tend to be tabulated together.
What was the top number there?
The top number for which what? W is 131 pounds per foot, and it equals 10.917 pounds per inch. And then, so that's part of it. And then, so V, do we need to do any conversions of the other one? The P is 2,000 pounds. The length is 288, and 48 times EI. So V from PL, or the point load, is 0.312 inches downward. So linear superposition, V total equals V distributed load plus V point load is 0.619 inches downward. And where does that occur? Where is that deflection in X? This is symmetric, so it's right in the middle. It's at 144. So at X equals 144 inches at midspan. So the next page in your course pack, I believe, is precisely like the other one that I handed out. I think I copied that directly. Yeah. So you've got deflections at particular places and slopes, which here it's noted as V primes. On your bingo card, they're noted as betas. Beta is V prime. That is slope. So what I'm going to do now, and this is not in the course pack, but it's a little bit of, well, like sort of a bingo game, to identify when these tabulated equations are relevant and when they're not. Oh, no. My friend, the spinny circle. So while my spinny circle is spinning, of course, I almost did an April Fool's on y'all, and I just couldn't do it. No, not a pop quiz. I had it all. I had it all figured out in my head. I was going to say, yeah, guys, I just got this email from the quality enhancement plan people. You know this class is writing intensive, right? Well, it looks like the way I've been running it, there weren't enough pages to qualify for writing intensive. So to get credit for the class, you guys are going to have to do 2 more reports before the end of the semester. And I decided that just wasn't very nice, so I didn't go for that.
I would never believe that.
No, I did. I got back to my office and I had completely forgotten about it. Like, I thought about it on the drive in and then forgot about it in my 10 o'clock lecture, and then I just decided that I just couldn't do that to y'all. Yeah, the wailing and gnashing of teeth. So, yeah. So there, that was my silly April Fool's idea.
It's all right, no, it's spinning.
Mm-hmm.
If it's not spinning, it's not spinning.
When it goes gray is when you worry.
It's still up there. It's not moving.
Oh, good googly moogly.
At least your timer's on.
Oh,
You just have to touch it.
Yeah,
Magic.
just touch the screen. It's predictable.
Right, it's a magic touch screen.
This bingo didn't work when we all have the same bingo card.
You're thinking way too hard about this bingo
Whoever
game.
answers it first.
Whoever screams out bingo card.
Jesus.
Oh,
All right, there we go.
all right. So, all right. If this is my scenario, and I want the deflection at the end, do I have one that would work?
29.
Am I going to have to shush you? Okay, so is 29 appropriate? 29 is the right shape, it's the right connection, it looks like the right load, and I have a Vmax. So that's an easy one, that's a gimme. Except
It's the negative sign. You never change the negative.
these guys. Oh. So sometimes, and going through these, you'll get a few cases that sometimes you can just split the sign, and sometimes it doesn't work quite right. Okay, so in this case, yes, it would just be upward by WL to the 4th time over ADI. It would just be a plus sign instead. All right? So, next one. I'll see if you've got the answer in your head, and I'll call on you, and we'll see if you get bingo or not. Can you get the deflection in the middle using the tables? What do you got? Okay, we think 11 and 2, and we can just add those up, and we'll get the answer. There you go. So that works because it's asking for the middle, and that's where, if you look at the little drawings, the beam drawing tells you where the Vmax is. All right. So maybe this is a kind of a lame bingo game, but can I get the deflection in the middle if this is what my loading looks like? You think we can?
Oh,
Yeah. Well,
Ooh.
don't you have to look at your shear and moment diagrams and then figure it out at that position?
Okay, so kind of, sort of. Okay, this is where I'm going to introduce this last equation column down here, the elastic curve. The elastic curve is your V of x that you would get if you write the moment equation and integrate it twice. The elastic curve is your deflection shape. So elastic curve is your V of x. Your elastic curve is your V of x. So in that case, you can't use anything out of the center column. You could for the distributed load, and you could use number 5, but number 5 gives you the deflection here. So it doesn't quite work with the tables, so you would either have to take 6 plus 11. No. Yeah. You would have to do 6 for x equals halfway plus 11. Does that make sense? No. Okay. Equation 6 is the elastic curve. So equation 6 is minus PVX over 6LEI times L squared minus B squared minus X squared. If I do this and substitute in, so this is V of X equals that. If I do V of 15 in there, that will give me the deflection in the middle due to that offset single point load. And then I can take plus minus 5 WL to the 4th over 384 EI for the deflection at the middle because of the distributed load. Does that help?
Yeah.
You're still got a wrinkly forehead.
No, I'm good.
Okay.
I'm just trying to figure out which equation.
So you say you plug the 15 in for both L's? Or
No,
X?
this is still the length of the beam. That's a length, not X location. This
Except for that.
is 30.
And
That
there
is
where you're-
15.
You pointed at that, and then I was thinking it was supposed to be where the L was, and then I was like, well, that doesn't make sense. But so, okay, sorry.
Good.
And it 6.
We
got
got it.
6 E.
Ah.
You said L.
We got it.
Where would
Yeah.
there be a case where you would use 12?
Where would there
Oh,
be?
if you were looking for it. at
Right,
20.
let's say we wanted V of here. Yep. Yeah. All right.
Are we ready for the next one? Are your bingo markers ready?
I don't know.
Oh, is this a new one?
Yeah, this is a new one.
Oh, I
It's
see.
a
Yeah,
cantilever
I
now.
see that. Yeah. Okay.
And it's cantilever.
Hmm.
You want it in the middle, or you want it?
Deflection at the end for the cantilever case. We have one vote for 30 and what? And 20? Try again. So 29.
Because 21 out of the end.
Right, so
It could be
24.
24,
24.
yeah, 24.
Look at 24 more carefully.
It's got two different equations though for where the L is at, right?
Yeah, for greater than L over 2.
Yeah.
Right, but look at where the load is. The load can only be halfway for that equation.
Your load can't be in an arbitrary place.
Oh, yes.
There's none.
So you could get it for,
You could use 29 to get the distributed load portion, but you have to integrate to get the contribution for this one. So you can shortcut and use it when it's the simply supported, but because equation 24 requires that that load be in the middle, you don't have a cantilever case in this set of tables that works for that kind of load.
What makes it different between the simply supported? I mean, why is there an equation for some arbitrary place?
Because of the displacement boundary condition at the right end, you could do it by geometry in this case if you said the beam was 28 long because it does not deflect. Oh, it does because you've got an extra load. Yeah, it's because, it just doesn't work.
it doesn't work, and it would be math to show you.
Where the force is in the picture.
Yeah.
You can't do it.
For the cantilever.
Right.
All right.
You can get a close approximation.
Yes,
But I mean, that's all we do anyway, approximation, right?
to some degree, yeah. It's just if the approximation is good enough or not.
Oh boy.
Does the moment have to be at the roller support, or can it be
Would that make a difference? Let me answer that one by saying, can it rotate about either one? It can't rotate here. The roller connection, it can rotate and it could rotate. So for that specific question, it doesn't matter. The fact that it is the roller versus the pin doesn't change how the moment will act because the structure is free to rotate on either one.
So there is no deflection in this
Well, it can rotate. If you grab onto a ruler, or if I grab onto this and I twist it, yeah, it deflects. There's no deflection at the end, but it certainly does deflect. Can you use 8? Where's my... Can you use 8?
Would it work?
Yeah.
Well, what is 8 telling you?
Leave
At the middle?
no.
No. What's going on here? When you do this, and I'm going to exaggerate it a little bit, if that's your undeflected shape, and you put, which way is that going? That's going to make a frowny beam. It's going to do something kind of like that. That's really exaggerated. Where the maximum deflection is not at the middle. It's closer to the applied moment. And it is at, in fact, root 3 over 3. So it's like just on this side of the center. So no, you cannot get the deflection at the middle. You can get the deflection at the maximum, but the maximum is not in the middle.
Why couldn't you use 9?
Why couldn't you use 9? You can use 9. You could use 9. Except which way, if you apply the moment on that end at that side, it's going to make a downward deflection, and this one is going to make an upward deflection, so you'd have to reverse the sign. But yes, equation 9 would work for this one, with x equals L over 2.
Moment at this end?
Can you develop a moment here?
Oh, I guess not.
Is there almost a question or a comment out there somewhere?
What does it do with the, like on the paper, it's got L times 1 minus. So it says at x equals L times 1 minus root 3 over 2.
Right.
So is it because we're at the other end?
Well, if it's either at root 3 over 3L, or it's at 1 minus root 3. I mean, it's just which end you're measuring from.
Okay, gotcha.
It's this far from the moment end, or it's 1 minus that far from the not moment end.
Gotcha. Yeah, that's what I'm saying.
Yeah. Yeah. Yes. Yes. Okay. Can we get the deflection at the end with that one using tables? No worries. That one's textbook easy. You don't even have to think about it very hard. It's just straight out of the tables, 29 and 20. And I think that's it. Oh, nope. Can we get the deflection at the middle? Same case.
We use our elastic curves.
Elastic curve, the sum of the elastic curves.
I'll say no.
No, for a variety of reasons. Because of the reference to the fixed connection, the fact that that load increases makes it completely different. The fact that the load doesn't go all the way to the end. And actually, this is a flaw in my little program, because I did say that 0 was at the end, but I guess it can't draw a 0 arrow. So, whatever.
What program do you use to make this?
Magic. It's the magic program. It is this thing called,
Which graph?
wow. Asked me and my brain evaporated.
I tried.
MD solids. MD Solids is the name of the program. Students can get a 30-day evaluation copy that basically you put in these beams. It will give you, and in fact, I was going to, or I always tell people right about now, because the 30 days last from now until the final, because it's a great study tool, because you can put in any kind of beam scenario. It tells you the cross-sectional stresses. I mean, you can do all of this stuff. It's called MD Solids, and I think that was the end one. Yeah. How are we on time? So I think it's on this computer.
I was just thinking about the lab report instead of making
And
Microsoft Word.
right.
'Cause that's fine.
No, it's not. And I own that it's not. Okay, it may not be on this one.
Where do we get it?
Google it. It's some guy has written it, like it was his hobby.
Oh, he doesn't know.
No.
You sure he wasn't motivated by the whack in PowerPoint or Microsoft Word? Maybe he had to write lab reports. He graduated. It's like my sole purpose in life.
So this is what MD Solids looks like. So if my bajillion windows. My brain is too full. Hey, it's time to go to class. Okay, so, and if we go back, you can do trusses, you can do indeterminate beams, you do determinate beams. So let's make a beam. Let's make it a 30, why is this not? So we'll make it a 30-inch beam, and we'll put the left support at 10 inches, and we do this. Uh-oh. No, it can't. Let's do this at 10. What's going on? 10 and 28. Okay. So there. Now it's at 10 and 28, and I had these other loads, and if I go back and let's put another bending moment, let's put it at 15, and sure, let's make it, we can mix some units, whatever. And it adds another bending moment, and it's magical shear and moment diagrams. Yeah, I know. I didn't tell you about that before.
How do you take a use that snippet screen capture?
Save bitmap as, and it ends up making one for the load, the moment, and the shear with whatever name, and it just plunks them into a folder. So it does your shear and moment diagrams, and then even better, if I go back.
I had this question since we started, or after we walked out of the lab, because I knew it was going to be a pain making these things work.
So if I then go to section properties, and I select, sure, this kind of flange, some sort of standard thing in compute, it gives you all of this stuff, and then I can apply that loading diagram to this cross-section, and it gives me the shear and yada, yada, yada. And it'll plunk it out in Excel.
That's how you figure out.
So, and then I go back, and I go, where's the, it's like,
Lecture.
It's like everything else in engineering. There's a program out there that will do it way easier.
so where, I guess because the screen resolution is so low, I can't get to the stress distribution.
Is this like an online, like you log in with your username?
No, it's just a standalone program that you can, that just runs. Yeah, more circle.
Are they on the school's computers?
No, it's, like I said, it really is this dude that's like a mechanics and materials professor wrote it, and it's his thing that he did, I don't know.
So did you pay to keep the, it's
To,
like a 30-day, you said a 30-day trial?
no, what did I do?
I'm
Yeah,
teaching this class.
or
too.
Dr. Howard said, email, I don't know. I got a permanent license for it.
No. Permanent license.
And I don't know if it was a purchase thing or if they'll just give it to faculty or I don't know. But it's quite powerful.
So if we want
That's
to-
the one. Normal stress distribution. Oh. Yeah. Anyway, if you get it right, you can define the loading, define the section, and then it will tell you the stress cross sections. And SolidWorks actually has the capability to do probably more powerful stuff than this, but then SolidWorks doesn't do the nice diagrams.
I've looked up.
So,
There's no like
yeah.
clean, easy way of doing
So, wow, I didn't need to record all of that gobbledygook in Integrity. Oh well.
Secret is out now.
No, I purposely wait until the 30 days, roughly 30 days before the final, so that you can use it from here on out to the end of the semester.
When homework is done, we have
Yeah.
like 32 level scenarios.
Yeah, that one. Yeah, true,
Model diagram.
true. But you have to understand it, how to do it by hand.